Okay, here we go. So, comparing two means. I'm not gonna spend a whole lot of time on this, but this goes through sampling distribution. The assumptions conditions are basically the same, with a few tweaks here or there. But similar also to proportions. Notice, okay, I'll point this out. We have the standard deviation squared there as part of our sampling distribution. Standard deviation. Okay. Here's the conditions for performing inference. Okay, so same thing as proportions. If we're taking random samples, then the two samples need to be selected randomly, number one, and the two samples need to be independent of each other. Okay, it could also be two groups in a randomized experiment. Okay, and then we have the 10% rule. And our normal large sample, the check for normality for means is that the sample size has to be sufficiently large. If not, then we need to check for skewness and outliers. Okay. However, if the population is approximately normal, then that doesn't matter. Okay, if we're talking about the sampling distribution. Right? So here's the formula for the confidence interval. We got x bar 1 minus x bar 2 plus or minus t critical value. And then notice again, I have the standard deviation of the sample. It's squared there. And the t critical value, and I'll point this out when we get to it. The degrees of freedom, there's a really complicated formula. Okay, so if you have one sample, the degrees of freedom is just one less than the sample size. If you have two samples, it's a pretty complicated formula, but we're not going to worry about that. Our calculator will do it for us to calculate the degrees of freedom. Okay, and so here's for a significance test. We've got t equals, and then we're going to do x bar 1 minus x bar 2, and then mu1 minus mu2 for statistic and the parameter, and then standard deviation. It's the square root of the sample standard deviation squared divided by the sample size, and for both of those. Okay, so I'm just going to go ahead and jump right in. This says a potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Kimberly Inc. The weights of potatoes from Riderwood Farms are approximately normally distributed with a mean of 175 and a standard deviation of 25. And the weights of potatoes from Kimberly are also approximately normally distributed with a mean of 180 and 30. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and they weigh them. So we're going to let x bar c minus x bar r be the difference in the sample mean of the weights of potatoes. What is the shape of the sampling distribution? Okay, so I said the shape of the sampling distribution of x bar c minus x bar r is approximately normal. And why is it approximately normal if my sample size is only 20? What does it say? It says what is approximately normal? Not the sampling distribution, but it says that the population is approximately normal. And so if the population of both of these are approximately normal, then the sampling distribution also has to be approximately normal. And it doesn't matter what the sample size is. Okay. If the population is skewed and the sample size is large, then we're okay also. But here it says that the population is approximately normal. So therefore, the sampling distribution is also. So I said it's approximately normal because both populations are approximately normal. find the mean of the sampling distribution. Okay, so we've got mu, and then x bar sub c minus x bar sub r. So we're just going to subtract the means. So the mean of the Kimberly was 180. And the mean of the Riderwood was 175. And so that's going to give me 5 grams for the mean. And part C says, find the standard deviation of the sampling distribution and show your work. Well, I'm going to check that the population of potatoes is greater than, it was 20, right? 10 times 20. And that is a reasonable assumption. And so if that's the case, I'm going to find sigma x bar sub c minus x bar sub r, which is going to be the square root. And then we're going to do the standard deviation of the sample squared. So it's a variance there. Divided by 20. And then the second one, it was 30. So take your calculator and put that into your little calculator. And somebody want to help me out? Sampling distribution, standard deviation. 8.732. 8.73. What I got. All right. Well, that's it for that example. I'm going to go on to the confidence interval. So, Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chips as name brand chocolate chip cookies on average. So to investigate, they randomly selected 10 bags of Chips Ahoy cookies and 10 bags of Great Value cookies and randomly selected 1 cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each, and here are the results. Part A says construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. All right, so I want to estimate the mean of Chips Ahoy minus the mean of Great Value. And so I'm going to do a confidence interval. So I'm going to do panic here. So let me define these. Mu sub CA is going to be the true mean number of chocolate chips in Chips Ahoy cookies. Cookies. And I'm going to say mu sub GB. It's going to be the true mean number of chocolate chips in Great Value cookies. Okay, and so we need to find X bar and S. So I need you to take your calculator here. And let's go to the spreadsheet. And let's put our data in. So go ahead and name it. So I called mine chips for the Chips Ahoy. Here I called this great value, GB for great value. And so you need to go ahead and put your data in there, please. And so now I need to get X bar and S for both of these. And you can do this two ways. You can run one var stats on each one. Or in this case, since they have the same number of data points, they're both 10, I can run two variable stats on both of them. So I'm going to do that. But if there's a different number, you can't do that. You would have to run one var stats on each one. So I'm going to go to menu, statistics, stat calculations, and do two var stats, and then select my variables there for each one. So I got chips and I got great value, and I hit OK. And so I'm going to get X bar. That's going to give me the mean of the Chips Ahoy, and S sub X is the standard deviation. And then if you scroll down, and I got Y bar there, that will give me the second great value mean, and S sub Y will give me the great value standard deviation. All right, so let me go back to the notes there and write that down. So I've got X bar of the Chips Ahoy was 18.4. S of the Chips Ahoy was 1.78. And then X bar, the great value, was 19.4. And then S of the great value was 3.6. All right, so here we go. Assumptions, conditions. For my confidence interval, what's the first one? Data come from two to what? Two keywords. Okay, it's got to be random, and if there's two of them, they got to be independent. So two independent random samples. Okay, and so it's given in the stem of the problem that they were randomly selected, and I think I can safely assume if they come from two different brands, Chips Ahoy and then Great Value, that those two things will be independent of each other. All right. Number two, 10%. So we've got the population of Chips Ahoy cookies and the population of Great Value cookies. Both of these things have to, and the sample sizes were the same, so I can do one for both of these. They've got to be greater than 10 times 10. And so that is a reasonable assumption. However, for the large counts, my sample size is 10. n equals 10 for both of them, n1 and n2 are both 10, which is less than 30. So I need to check for skewness and outliers. All right, so I'm going to go back to my calculator here. And I am going to add a page. So let's go Control, Doc, add data and stats. And then we want to click to add variable, and I'm gonna put the Chips Ahoy on there, and it looks okay, I think. And then I'm going to go to menu, and then I believe it's plot properties, and I want to add an X variable. So I'm going to select that one. Let's see if I can. Oh. Yeah. That'd be great for the video. There we go. Oh, gee, the stats gods are angry at us. Okay, you want to click to add variable. Put in the grade value there. Okay, and so then we have our two dot plots. And I would say that both of those are fairly symmetrical with no real outliers. And so what do? We show that on our paper, right? So let's go back to the notes here, and let's make a little sketch of the dot plot. Make sure that you scale it and make sure that you label it, and then put your dots in there. Got the grade value. Looks like that. So I got the Chips Ahoy here. Looks like that, something like that. Statistical work of art here. And so then I'm going to say no obvious skewness or outliers. So normality is established for a T procedure. Okay. All right, so this is a 99% confidence interval for two sample means. This is a T interval. All right, can we do the formula without looking? What's the center of the interval?
X bar 1 minus X bar 2.
All right. What goes next?
Plus or minus.
Plus or minus? Plus or minus what? T critical value? What goes next? Square root of standard deviation squared. Don't forget the squared, okay? So S squared over N1 plus S squared over N2, referring to the standard deviations of, that should be, there's a 1 and a 2 there also. All right, so let's fill those in as far as we can. So we've got 18.4 minus 19.4 plus or minus. And so for now, I'm going to give you the degrees of freedom, and then I'll show you when we run the confidence interval, it will give it to us. But we're going to do inverse T. Inverse T. Okay, so it's going to be 0.995 because that is the area to the left. It's a 99% interval, which means I've got 99% in the middle and then 0.5% on the left and on the right. And my degrees of freedom in this case is 13.145. Okay, so put this into inverse T. And like I said, we're going to use technology to get that DF because it's combining the two samples together. And you should get 3.007 here. So I've got plus or minus 3.007 and then times the square root. And we've got 1.78 squared over 10 plus 3.6 squared over 10. Okay, so set it up. And then we're going to go to the calculator. And I'm going to go back to the spreadsheet here because I want to import the data that's already in there. And so you must do that from the spreadsheet. So here I'm going to go to menu and statistics and confidence intervals. And this is a 2 sample T interval, option number 4 there. And I'm going to import the data. And then select the variables. So I got the Chips Ahoy. And I got the grade value. And then I've got to change my confidence level to 0.99. And then it's going to ask you whether you want to pool or not. And so for right now, we just say we are not going to pool. No, don't pool. Okay, maybe we'll talk a little bit about that later, but for right now, no pool. Okay, so pooled is no. And then I'm going to hit OK. And let me scroll up there. So I've got my lower bound, I've got my upper bound. There's my degrees of freedom, which I used to find inverse T. It was 13.145. So let me go back to the notes here and write my interval. So this is negative 4.82 and 2.81. So my conclusion is we are 99% confident that the interval from negative 4.82 to 2.81 captures the true mean difference. and the number of chocolate chips. Chips Ahoy. And great value. And so the last question here says, does your interval provide convincing evidence that there is a difference? And the answer to that is
No.
no. Why not? 0 is included in the interval, which is a plausible value. So there is not convincing evidence. So because the interval contains 0, there is not convincing evidence. So after buying many helium balloons, only to see them deflate within a couple of days, I hate that, Aaron and Jenna decided to test if helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into 2 piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after being filled, and then again 3 days later. The average decrease in circumference of the helium-filled balloons was 26.5 centimeters with a standard deviation of 1.92 centimeters, and the average decrease of the air-filled balloons was 2.1 centimeters with a standard deviation of 2.79 centimeters. Do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? Okay, so we're gonna do a 2-sample significance test for means, t-test. So let's define our parameters. I'm gonna let mu sub h be the true mean decrease in circumference of helium-filled balloons after 3 days. And mu sub a is going to be the true mean decrease. And circumference. And air-filled balloons. After 3 days. All right, so let's write down some of the information they give us. We got X bar sub H, and that was 26.5. And S sub H was 1.92. X bar sub A for the air-filled was 2.1. And S sub A was 2.79. All right, so my hypotheses, my null hypothesis, mu sub H minus mu sub A equals what? Equals 0. That there is no difference. Whoa. That there is no difference. Okay, and so my alternative hypothesis is going to be mu sub H minus mu sub A is what? Is this one-sided or two-sided? It's one-sided, okay? Is it greater than or less than And that's going to depend on the stem of the problem. So it says, do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? And so this is going to be greater than 0 because I'm measuring the amount that it decreased. And so if helium is greater than air, which is what the stem of the problem said, then this will be a positive value because the helium decreased more, if that makes sense. Okay. Assumptions, conditions. And okay, careful, because this is not a random sample. Why is it not a random sample? What? I'm gonna go back here. Let me go back, scroll back. Where we go? Right there. Says the data come from 2 independent random samples or 2 groups in a randomized experiment. And so that's what this is. So I'm going to say data come from 2 groups in a randomized experiment. 2 groups in a randomized experiment. Okay, that's given. And the 10%. Not necessary. Why not? Does the population have to be 10 times the sample? No. Why not? There is no sample. Okay, so make sure. Okay. For example, on the AP exam, you cannot say that it is a simple random sample if it's not even a sample. Okay, if it's an experiment, then you have to say it's an experiment, okay, 2 randomized groups. Yes.
Yeah, you still have to say it's independent.
I don't think that matters in this case because it's an experiment. Okay, yes.
Would we get points off if we still did like population is greater than?
That would probably be ignored. Okay, but I mean, you're wasting time. You don't need it because there is no sample. Okay, so not necessary because it's an experiment. All right, so check for normality. N1 was equal to 30 and N2 was equal to 30. So normality condition is met. 30 is greater than or equal to 30. Okay, and so this is my name 2. Okay, so ironically, what's the name? 2 sample t-test. So let's say 2 group t-test for means. I'll put sample here in parentheses. All right, can we do the formula without looking? T equals. What's my statistic? X bar R1 minus X bar 2. Minus, what's my parameter? Mu1 minus mu2. And what's my standard deviation here on the bottom? It's going to be the square root. All right, and we've got the standard deviation squared over N1 plus standard deviation squared over N2. So, yes,
So it's always gonna be a t-test for means in this, in the two samples.
I mean, I hate to say always, but almost always, yes. Okay. Mhm. You rarely use a z-test for means because, I mean, it's not outside the realm of possibility, but you rarely know the standard deviation of the entire population, much less for both, if you're comparing to them. So it's almost always a t-test. Okay. So let's fill these in. We got X bar 1, which is 26.5 for the helium, minus X bar 2, which is 2.1. And what is mu1 minus mu2? You got nothing? That was clever, right? It's 0. Why is it? Give me a little bit of credit, right? Why is it 0? Look at your hypothesis. What, right? What's your null hypothesis? Mu1 minus mu2 is 0. Okay. So then gonna fill in our standard deviation. We got 1.92 squared over 30 and plus 2.79 squared over 30. And now we're gonna go to our trusty old calculator. And so I'm going to go to the scratch pad here and go to menu, statistics, stat test. And then this is a 2-sample t-test, which is option number 4. I'm going to write in the stats, not import. So X bar 1 was 26.5. Standard deviation was 1.92. Right, the group was 30 and the X bar 2 was 2.1. $2.79 and second group was also 30. And again, it's going to ask you if you want to pool or not. And we say no pool. But I need to change. Don't forget to change your alternative hypothesis. We want mu1 is greater than mu2. Okay. And hit OK. So look at this. Here's what I want you to do. Raise your right hand, please. And repeat after me. I do solemnly swear that I will not make a careless, and forgive me for saying this, but stupid mistake
Forgive me for saying this as stupid mistake.
of writing down a p-value
Yeah, p-value
of 1.98.
of 1.98.
Why would that be a careless and perhaps even stupid mistake? First, what is a p-value? It is a probability. Can you have a probability that is greater than 1? No. Probability has to be between, reviewing unit 5, right? It has to be between 0 and 1 inclusive. So can you write down the probability is 1.98? No, that doesn't even make sense. Okay. That's the first thing. The second thing is, right, 5th grade math, scientific notation. This is 1.98 times 10 to the negative 40. Which means there's 39 zeros in front of the 1, the 9, and the 8. So please, I will swear, I will pull out my hair. If you say something like the p-value is 1.98, so it's greater than alpha, therefore we fail to reject H naught. No, it's not. It's 39 zeros. And then a 1.98. My stats ran is now over. Okay, so back to the notes. And I'm pretty disappointed collectively in third period that you didn't say, well, where's your decision rule, Newhouse? Yeah, oh, no, now you say it, right. Sure, you don't wait when I'm in the moment, you're like, oh, let me place a bet on the game after it happens. Yeah, good one. Whatever, here we go. My T value here is 39.46. My P value is 1.98 times 10 to the negative 40, which is 0, of course. And let's go up here to my decision rule so that we don't lose points, right? I'm gonna let alpha equal 0.05. All right, and then we've got a T critical value. This is only one-sided, and my rejection region is greater than T. Why is it greater? It's got to match up with your hypothesis, okay? So there's 5% right here. And so I'm going to let inverse T equal 0.95, and then I'm going to get the degrees of freedom from, again, use technology, okay? When you run the significance test, look at the significance test on there. I think it was like 51.145, is that right? So if you do that, you're gonna get 1.675. So I'm going to reject H naught. If my p-value is less than alpha and my T is greater than 1.675. Yes,
If we have to get the degrees of freedom for the significance test, should we do significance?
I would do it and then just go back and write it in. It's fine. But I mean, technically, you can always say, we're gonna reject H naught if the p-value is less than alpha. That's fine. Okay, so since p-value is less than alpha, we reject that H naught. Saw a bumper sticker on the truck that said that one time. It's the small things in life. Okay, so we say there is sufficient statistical evidence to conclude, and then put it in context, helium balloons deflate faster than air-filled balloons.